Okay, so in our last class, we discussed about the first few things about the chapter moment. We're continuing that lecture from that point onwards. We took some time to reschedule one of our classes, so that's why the recording is starting a little bit late. So let's get going. The first thing that we'd like to take care about is reaction force. So I'm going to talk about this first. Reaction force. How do we, why is this important? So let me just give you some very basic idea. Let's say we are provided a very simple scale. These are called, they're not called beam balances, but they're sort of like a beam balancer. So let me just draw up a figure. Let's say we have this is typically how a moment balance looks like. Moment balance জিনিসটা কি সেটা আমি তোমাদেরকে একটা ফিগার দিয়ে দেখাচ্ছি। Let me just are all beam balances. This is a very good imagination. Where's the moment balance? This is a spring balance. Let's talk a little bit about this this one. Can I search similar figures? This one. Yeah, this is a good high definition image. So let's copy this and let's talk this thing a little bit. Okay, I'm gonna use the right column side. So on the left column, I'm gonna do some math. So let's have a look at this figure and try to understand different parts of it. Here's what I need you to understand. This thing is what we call, sometimes it's called a moment balance, sometimes it's only called basic balance. This thing works upon the very simple basic of balancing moment. These devices can be adjusted or calibrated upon requirement, and they can be used to measure a lot of things. The very simple type of balance that we know is what we call a beam balance. Beam balances are the most simple version of any type of balance. Beam balances look like this. We have a long beam which is uniform. At the center we have a hanging rope, and there's a pivot. On the two ends we have two identical what can I say, hanging pots which we use to put stuffs on. And the concept that beam balances work is that if we put some unknown mass over here, and if we put some weighing stones that we know the values of over here in such a way that whenever we lift this up, the beam becomes horizontal. That tells us that these two masses are equal. The reason these two masses would be equal is because of the very simple thing that a very simple beam balance, which is that this thing is made in such a way that this length and this length are exactly equal. So if I write that, let's say this is D, this is also D. So if the beam is perfectly horizontal, this means the anti-clockwise moment produced by this mass and the clockwise moment produced by this mass should be exactly equal. That's what causes the equilibrium to be achieved. So that would mean, let's say this is the unknown mass. So let's say this is the weight of the unknown mass. Let's say this is the weight of the weighing stones. So I can write in terms of the principle of moment that W of the mass, unknown mass, multiplied by D should be equals to, this is the anti-clockwise moment, should be equals to the clockwise moment, weight of the weighing stones multiplied by D. DD crosses out, and if we just elaborate this formula of mass of the unknown mass multiplied by G equals to mass of the weighing stones altogether multiplied by G. GG crosses out, which ultimately makes these two variables equal to each other. So this is a very simple case of the imbalance. Okay. Apparently, I have forgotten to pay the subscription fee for Zoom, so this class will be interrupted after 10 minutes. I'll give you another link and I'll upload the lectures in parts if required. So, no big deal. So এই দুটা হচ্ছে দুটা সিম্পল জিনিস। আর এই স্কিলটা যে মেকানিজমে কাজ করে সেটা হচ্ছে, over here we have a plate on which we're going to place our unknown object. This plate is designed so that it will always be horizontal. There is a certain mechanism that will keep it horizontal. That mechanism is actually this small thing. Do you see that there is a small black cylinder that goes through the whole of this blue structure? Do you see that there's a small tiny hole over here, shaft over here? Yes. This thing actually goes through a very tiny, almost frictionless hole, just to make sure that this bar remains horizontal. Always, this plate is always made sure to be horizontal. Right over here, this black part that you see, which is not so well visible, so maybe I can go check for another figure. For example, if you look at this figure over here, this is the point. This is the point where there is a very sharp knife-like edge on which this entire structure stays. This entire structure is actually, we can float. I'm using the word float to give you a bit of an idea. Let's say if I just copy this image because this is a bit horizontal. What I mean that we can actually lift up this much part from the brown color frame. We can simply, this part is our one frame, which is the horizontal frame, and this whole thing that is above, outside this frame, this whole plate, this black structure, and all of these measured scales, we can altogether lift it up, and this whole thing is supported right at this point over a very sharp pivot line. And the idea is that it is already connected with some masses over here. If you see over here in this figure, here we have different scales. Have a look. This is a pretty large mass. You see that this mass is hanging over here at the zero. There is a small triangular mark, and this mass is actually pretty large. You can see that this mass is actually this much. I mean, this is the extended part of this mass, so it's a pretty heavy mass. And this line over here, which has multiple different edges, or wedges, let's say it has marked places onto this bar on which we can actually make this thing become perfectly horizontal. And this line is not actually, what can I say? I mean, this bar is not graduated. For example, you can see that, I mean, this mass and this mass, they should be always placed onto these marks. Any of these marks. Do you see those creases on the bar? Small creases. This one. Do you see this? একটুখানি dent আছে এখানে. Do you see that dent?
Yes, sir.
Yes. So we can move these masses to the right and place them exactly on. So for example, whenever we are going to place this mass right over here, this is going to read perfectly 0. This is also reading 0. And there is a small mass over here, which can be moved gradually over a pretty tiny scale. And the way this thing is, and over here, right over here, there is an end point, there is a very sharp horizontal line, and there is a sharp reference position that is marked with this over here. Our aim is to measure some unknown masses. Now, if you wonder that, what are these? I mean, what is the purpose of these stuffs? These stuffs are used to calibrate the device. Calibrationটা কিভাবে করব সেটা আমি একটু পরে বলতেছি, but we don't usually use this to actually measure unknown masses. এই তিনটা purpose আমি একটু পরে বলতেছি. The way this beam balance works is that whenever we will place all of these individually marked masses, large mass, middle mass, and small mass, whenever we're going to place all of them exactly to the 0 mark, and we place nothing on this top, it will be managed in such a way the total amount of weight on the left side, I mean, the total amount of weight of this bar. So now consider only the black part of this beam. So if I just cut it off, let's say, how can I select this freeform selection? Let's say, so now, whenever we place everything to the perfect 0 mark, this thing is designed in such a way that about this pivot structure point, about this pivot point, the weight of this whole thing on the left and on the right, altogether means on the right, you can see that apart from this moving weights, we have the whole scale over here, this pretty long structure. We have this additional markings part. On the left side, we have this plate, we have this additional screw that is visible over here. I'm going to talk about the purpose of this screw as well. And then we have this whole heavy mass, which is responsible to provide structural support for whatever we put in. So this thing is made in such a way, it is precisely manufactured in such a way that when we place all of these individual sliding masses on their 0 mark, this beam should be perfectly horizontal, and these two lines should perfectly match with each other. That's what we can say. The device is properly calibrated and it's ready to use. So at this point, we have equal weight on both sides with respect to the pivot point. So let's say this one first weight and this part weight is exactly equal. The way we utilize this device is that whenever we will place, let's say, some unknown mass over here, unknown mass place করলাম. So the moment we're going to place this mass, this part is going to go down and this lever is going to start going up using this pivot point. This shaft that you see, I just covered it. Do you see that there is a small tiny mark over here? Looks like a stamping pin. Do you see? This is actually the support, and there is a small pin that is seen over here. The pivot actually runs over this pin. So about this pin basically works as our pivot. So this is our pivot line, vertical line. If I draw it, the whole thing can all rotate out. So whenever we place some mass over here, this side goes down, this side goes up. So whenever this side will go up, this marking on the scale and this marking on the structure, they are not going to be aligned, which tells us that we need to rebalance the structure. The way it works, we're going to shift these masses to the right, and these two should only go in the designated places, and then we can gradually move this part by part. And by trial and error, how do we do the trial and error? I'll explain that. By trial and error, we're going to make sure that these two sides will become balanced once again, so that this beam side, this right side, will once again align with this mark. And whenever that happens, we'll simply add up all of the readings of these 3 scales. This one, this is scale number 1, scale number 2, and let's say scale number 3. We'll add up all of this 3 reading, should be the equal of this one. The advantage of this whole scale is that we don't have to have any individually weighing stone, typical beam balance. But in this case, we have all of those masses that is attached with the device. So once it is properly calibrated, I mean, students don't need to have access to these things. These things have a different purpose. Once this device is properly calibrated, this can be used for an indefinite time, for as long as the calibration holds true. We can use it to measure any mass that is within the range of this device. And how much is the range of this device? বাট বেসিক ব্যালেন্সিং এর পার্টটা বোঝা গেছে কিনা, যে রিডিংটা কিভাবে হয়।
Yes, sir.
ঠিক আছে, আচ্ছা এখন রিডিংটা আমরা কিভাবে করি সেটা আমি তোমাদেরকে বলতেছি। একটা জিনিস খেয়াল করো, try to understand the graduation or the breakdown of this scale. The maximum that this large mass can give us a reading is 500 gram out of scale number 1. So a scale max value কত? 500 gram max. So if we push it all the way to the right edge, we're gonna have a reading of 500 gram. The maximum reading that this scale number 2 can give us is 100 gram. This is the maximum value that it can have. The maximum that this scale number 3 that we can have, this is 10 gram max. 10 gram max. So the maximum measurement that this device can allow us to do, when all of these things would be placed to the very right and some unknown object over here will be balanced. So the maximum measure that you can do is how much? 500